In this video we are looking at constructing dodecahedron and the icosahedron based on this setup. So for you people out there interested in geometry, you know that these are these shapes are two of the Platonic solids. If we look at Wikipedia here, for example, we have 5 of them. What is significant with these shapes is that they have this is a way of tessellating a sphere based on the concept of that each facet, each part of the tessellation should have the exact same structure. So, for example, if we look at the two we're talking about, dodecahedron and icosahedron, the dodecahedron has pentagons, and they are all have the same length of the sides here. And that goes for the icosahedron as well, except that it is built from triangles. In this case it's 20, and in this case it's 12. Hence the name Dodeca and icosa, which mean 12, and which means 12 and 20. If we then scroll down, we can see that there have been vast analysis of these shapes. For example, here we have a construction method, which means that three rectangles are placed in this manner, and the dimensions of them are 1 and the constant golden ratio, which is 1.618 and so forth. So if we build these rectangles in this manner, which is as in this picture, we can then connect the corners in order to construct the icosahedron and the dodecahedron, because they are dual shapes actually. If you want to study more on that, you will see that you will soon encounter that fact that they're actually dual shapes. So here you see an overview of duality, what it means here. For example, the hexahedron and the octahedron. And we looked at here's the dodecahedron, which actually the center points are equal to the corner points of the icosahedron. So what we then have here is I already built these. We're going to build this from scratch soon. So here you see the constant phi, which is golden ratio, which then goes into facets, which you can find on a mesh, and facet dome, which is a little script that makes a facet directly on top of a point, so to say. So from a point collection, it draws a wall until the next point comes and makes a flat polyline. I can demonstrate that by highlighting this. So you see here is the point. It starts drawing a facet or a polyline based on a center point, but it adapts to the neighboring adjacent points, and in this way we can construct a perfect dodecahedron like this. If we then instead use the corner points from the dodecahedron, we have a different situation. I'll show you that here. Here are the corner points. What would then happen? It would build a triangle here, right? Because it wants to build walls perpendicular to the next point. Very much like also the system in a Voronoi pattern actually. That facet would then look like this. We can take on a boundary there to show you that it turns into an icosahedron, and then we have also its dual, the dodecahedron, hidden underneath. That is one part of this video. Then we also have the orient function, which is quite interesting. I have now extracted one of these triangles and flattened it so it's positioned here. And then if I start to build a pyramid or a tetrahedron shape from this, not exactly a tetrahedron, but with the various height, I can pull that up like that. I have a little slider down here in the right corner. That will get transferred to the shape we're talking about. There. So now all of these are moved to the shape that I showed you before. And this is based on different planes. So this is the orient component from a base plane to a target plane. And if I then start transforming my shape, everything will go accordingly. I can also swap shapes and use the dodecahedron instead, like this. And I pull up and you see the same thing happens there. And this, of course, is an example, so you can use this in for various structures. Another thing you can do, if I take that off again, you can also place, of course, whatever on it. So here are, for example, circles. You can resize and then actually then cut holes into the shape. Yes, so let's build this from scratch. So as I told you, it's very good to go online and read about these shapes before, which gives very much insight also into various polyhedra, which also leads to building, for example, geodesic domes and things like this. So first we need to construct those rectangles. So if we double click and type rectangle, we have on default we are on the XY plane, as you see here. One thing which is quite interesting, if you take out and visualize that rectangle like this and hide the rectangle component, you see that it's centered, right? And if you hover on the X and Y input, you see that the code is written -1, 2, 1, and -2, 2, 2. So this TO, the 2, actually signifies or means that you're using a domain. And the domains are to be found here on maths and domain. You can construct a domain like this. And then if you hover here, you see that it's the same type of code coming out, so from 0 to 1, for example. And we want to have -1 to 1, or maybe preferably 0.5 to 1, minus 0.5 to 0.5 for one direction, and then go duration the other direction. So if we go to parameters, take out the panel here and simply type 1, that's the first one we're going to use. And if you double click and search for golden ratio, there you have the constant. You can hover here, you see there's a lot of decimals coming in. So we need to construct a domain. What I usually do, in order to keep the proportions here, I divide these two in half. So I can copy this parameter, the panel here, and I type 2, and I go to maths and go to division. There, I have divided it in 2 already. And why do I do that? It's because if you hover, it's 0.5, like I said before. So I want to have a negative input in the A, so that this will be centered. Otherwise, it will look like this, if you know what I mean. So I want it to be on both sides, so that it starts constructing from the center here. So I will double click and type negative and use the negative component here. It's on maths and operators, and I will use the half, the division in halves here, division in 2, put that into the A, and now you can hover already. You see it's minus 0.5 to 1. Then I can take the positive 0.5 from here, and then you see you have already a domain from minus 0.5 to 0.5, which means the outcome is 1. If I put that in, I can also measure it here to illustrate that. Something like that. You see it's now 1 millimeter. We are drawing now in millimeters just for an example, right? So this looks quite much. You can select all of them, and then you can right click and take cluster, and then you can name that something, for example like 0 division 2 DOM. So now I don't have to do it again when I am using my next parameter, which is golden ratio. So I'll copy it and put that into the Y. This is then, if we look from the top view, this is a golden ratio rectangle. So I measure here, it's 1.61, and here it's 1, which is absolutely correct. So now we already have the first rectangle. We need to construct the rest of them. What we can do, we already have the parameters, right? So we can copy these, and we simply need to do another plane, because as you know, the plane here is world XY on default here as well, of course. So if we go to vector and to planes, we should simply select something with a Z on it, so that we draw on in the Z axis. So let's take XZ and test with that. Let's see how that looks like. We can also hide the plane. You see already where you're gonna draw, right, if you take out the plane. So that was almost correct. The thing with this shape is that the edges should not touch. Otherwise, if they do, it's a completely different shape, of course. So they should be inserted into each other. They should not be touching or intersecting in the edges. So what can be wrong with this now? It is simply a matter of swapping X and Y. So we swap, and there you go. Now they are combined. So we can copy the first one again here to get the third triangle, and you already know probably which plane we're talking about then, with the YZ plane. So now you draw in this direction. This time is going to be correct also with the rectangle there. Okay, so we have the triangles already. What we need to do now is to extract their control points by double-clicking control points and attach that to all of them. Remember now that when that comes out, it's 5 of them. Why is that? It's because they draw, a polyline is drawn like this. 1, 2, 3, 4, 5. Or rather 0, 1, 2, 3, 4. So it's 5 points. That means that we have a double point, and that's going to mess up the facet dome quite much. So if we double click and type cull points, cull duplicates, this takes away double points. So select that, insert it, hover, 4 points. Now we can copy this and attach that to the rest of the triangle rectangles here, like that. Yes, and now the setup is more or less finished actually. We need a mesh, we need to go to triangulation and a facet dome, and then we insert all the points in the P, like that. 12 perfect polygons. The interesting thing here now is that it's dual, right? So we already have the dodecahedron. To achieve the icosahedron, we need to take out the control points of this shape. So, we can copy one of these and take that in. Now we have all the control points. Remember now that the icosahedron has 20 faces. So let's see if there are 20 points, otherwise there could be a problem. You see, it's actually 60 points, so it's double points all over the place. But if we flatten this input and then hover, it's 20. So then we can copy the facet, take that in, and then we already have a perfect icosahedron. So that code is not so large, actually, quite interesting one. So I usually divide them like that, so I know that that belongs to the dodecahedron, that belongs to the icosahedron. So what we can do now as well is to double-click and type boundary surface. So, and that then I visualize how you can turn these into solids. And you probably already know that if I type brep join and attach that both, like that, it's a closed polysurface, closed brep already. Okay, so I'm gonna continue to work with one of these and make an orient so that we can map objects onto the shape. So what we need then is to look into how the orient works. If we double click and type orient, here it comes already. It's also located on transform Euclidean. We can remember to always hover the component. So first we hover the orient, the text here. Orient an object. Orientation is sometimes called change basis transformation. It allows for remapping of geometry from one axis system to another. Sounds pretty good. The first input is base geometry. That's the geometry that's going to be moved or reoriented, repositioned, reoriented. And the source is the initial plane, which is world XY on default. And we have also final plane, which is also actually world XY on default. So we should put something in here, and we should start playing around with the planes. But then we have to construct planes, right? So if we, for example, now take, we can, by the way, hide this one, right? Otherwise it's double geometries and it's turning very red, you can't really see anything. So first we can construct these as planes. So that goes pretty fast actually, because any closed object, any closed polyline or surface, a flat surface, can be turned into a plane. So if you go to parameters, geometry, and take one of these representative components here, plane, it will understand that surface as a plane. So take that out, take the boundary, and then we attach it. Then it turns into something that looks pretty crazy, but that is because all the planes are there. It's 12 planes. So if I hide that instead, and we have to look at it, look at one of them to explain something here. So I take list item, which is, which is on default 0, so that means I will take one of the planes. You can hide the orient also. So here is one of them, and you see that there's a thicker green line and a thicker red line, right? So this is what happens when you turn a surface into a plane. It uses one of the corner points for its origo, or its center point. It's 0, 0, 0, which is not really so good if we start to draw something in the middle of another plane, which is recommendable to know where things are. We need to have this in the very middle of this pentagon. So we can actually reposition the plane so that it lands on the pentagon, and I'll show you how to do that. You go to vector, you go to plane, and then you take plane origin. For example, there's very many methods to do it, but plane origin is very good here. Which means then we can hover the inputs. Base plane, we have one already. Well, let's take this one as a test, like that. And then we need a new origin point of the plane. Otherwise, nothing's going to happen. So let's extract the center point of this pentagon. Double click, type area. We measure the area. We automatically get a center point, and the area component is on surface analysis. and the center point goes in there, and then you have a completely different situation, namely that the plane lands in the center of the pentagon. Sorry, not the pentagon. It should of course be like this. You have to measure the pentagon itself. I accidentally took in the plane there, so here, this one is supposed to be measured like that. See, I don't want to create confusion, so I used the boundary in a list item. I extracted the center point from the list, from the surface. This is the surfaces, and the plane is simply going into the B here. Yeah, so now we're only doing this with one of them, right? So we can simply skip the list items and put everything in from here. Okay, so first, if we skip this list item, the boundary goes into the geometry there, and the plane goes directly into the B. So now we have 12 planes, and they're all in the center of everything here. It looks very messy, of course, so I recommend you to shut that out, like that. Okay, so now we actually have something already. So, for example, if I draw something here on the plane, like that, I take that in as a test, and I use this as a target. It all lands all over the place like this, right? Because these are our target planes now, the final planes, which we use for relocating things. So anything I draw here will be transferred to the surface. And why here? It's because the initial plane is world XY, which means that we are using anything that is in 0.0.0. So if I were to move this away, they will move away as well and leave the shape completely. It mimics anything that happens on this XY plane with in relation to 0, 0, 0. This means that we can actually construct another source plane. For example, we can create a plane somewhere else. We can have, for example, we take vector and an XY plane like this. It's the same plane, of course, but we can, if you right-click on the original plane, set one point, we can put that whatever we want to there, for example. So now anything we draw here using this as a reference will be moved. So do you follow? So if I'm drawing on this plane and using it as a source plane, initial plane, then the system understands from where to take something and to where to put it, because the target planes are there, right? We have one problem here, though. We don't really know the extents of each and every plane here. So what we can do is to swap this direction. So we take one of these boundaries and put it on this plane, and then we transform it from here and shoot it back. So this is a quite interesting little experiment that I will show you now how to do. So given given the fact we have 12 of these facets of the dome or the sphere, which is also called a dodecahedron, we need to it would be good to have the extents, the limitations, the limits in here in which we can draw and then put something back on top. So we can then copy this orient piece here, and then we can extract one of these facets. Actually, it's better, of course, to work with the with the polyline or with the surface. It doesn't really matter. It depends on what you want to do. So let's take one of the surfaces here. So we double click and type list item, and it's on 0, as you know. And then we need to create another plane. It can be, now it kind of turn into quite many planes here. What we can do is to copy these, turn that into a plane, and extract the C. And then we have already a plane exactly only for this one. We need to create a specific plane for this facet. So now you see that there, and then we can use that as the initial plane instead. So let's simply take these out. This is my initial plane, and this is my starting plane. Right? My target plane, I'm sorry. So now it's going to be transferred there instead. And what is going to be transferred? This piece. So if we put that in there, it lands perfectly on this one instead. And now we can do the reverse effect. So anything we draw here can go in here, so to say, back to the shape, but all over the place, of course, because here we have 12 planes. So, as only an example, you can draw whatever you want here, really. You see the setup is already there. It's sharing the same plane. In one case, it's the initial plane. In the other case, it's the target plane. Right? And here the target planes are the whole shape. And here the target plane is, of course, here where we draw something. So if we, for example, draw a circle here somewhere and take that in by parameters and set one curve, and then we take that into the orient, it's going to land all over the place here. By the way, this plane here we can take out so it doesn't really, it does actually disturb visually a little bit. So here you already have, if I move it like this, what happens then? You see, you can start playing around with that a little bit. Now you know the limitations here. So another interesting thing here is that you can very easily then make a stellated dodecahedron or stellated platonic solid. Here, for example, is a stellated octahedron. You see, that means that you simply pull out all of the, you extrude it to a point, more or less, all the facets. So, here I already have a geometry, right? In the orient box, it's this facet that has been transferred. So if I take extrude to point, for example, I can use it to simply pull up something which should be the center of it, of course. So we need to take out the center point by double clicking, searching for area again. Then we create the point, and then we take, you see the point landed in the center here, and then we have to pull it upwards. So we double click and type move. And we move the center point, and this is the point that's going to go in here into the extrusion. We need to have a C direction here if we want to go up, or whatever you want to do, actually. And now we can attach it already. So now you have a sort of five-sided pyramid here, and we need to have also a slider, of course, to affect the height. And it goes in there, and you can pull up and down like that. And then, oops, sorry, this extrusion is simply to be put into the G here, and then it lands all over the place on the icosahedron, on the dodecahedron, like that. And then if we pull back and forth, we see that it gets stellated. A perfect stellation, by the way, is when this line is completely straight, which it's not now. So there's actually online there are calculations, so you know exactly the angle that you need. But for this example, I don't think it's really needed to go in exactly on what digit should be in the slider right now. Interestingly, this setup, of course, is not only for platonic solids. I can move this here instead. It can be applied to quite many shapes. For example, we can also swap this so that we use it instead for the icosahedron by simply rearranging everything here. A quite fast thing to do that is that you see that you have a boundary here as well of the icosahedron, and everything is now controlled from this component. So I want to plan my algorithm so that it's so easy as possible. So here we have a lot of surfaces. So if we instead go to geometry, surface, and we just replace things like this. Then we can simply swap shapes. And if I do that now, everything is going to be affected. This is going to turn into a triangle, and all these stellations is also going to be adapted accordingly. So if I just pull that in like that, you have already a stellated icosahedron. So I can toggle between these two in a very easy way. Okay, so I encourage you to play around with this, not only using these stellations or platonic solids, but with very many different shapes.